Welcome. In today's lecture, we will be covering part 2 of chapter 21 on enols and enolates. So at the end of last lecture, we looked at the aldol reaction, which is when we take an aldehyde and react it with sodium hydroxide or a base to create an enolate, and that will then act as a nucleophile to attack another molecule of the aldehyde, which is the electrophile. In some cases, we can take two different ketones and aldehydes and react them together in what is called a crossed aldol reaction. Now this gets complicated very quickly because since we have two different potential starting materials that can become nucleophiles and two different starting materials that can become electrophiles, we have a possibility of up to 4 products as shown on this slide. In most cases, we don't want to try to obtain our major product by separating it from 3 other products, but there are some ways that we can minimize the number of products formed. The first is to use a substrate that's relatively unhindered and without alpha protons. So in this reaction, we could use formaldehyde, and this means that formaldehyde will not form any enolate because there's no alpha protons. And since it's sterically unhindered, it'll become a better electrophile. So if we mix these two aldehydes together in the presence of sodium hydroxide, we would only obtain this product where the enolate is formed from propanol and the electrophile is formaldehyde. And this is only going to be possible when we can only form one enolate and the other compound reacts with the enolate faster. So this is a relatively specialized variety. The other option is called a directed aldol addition. And in this case, we use LDA as a base and react it with just one of the ketones or aldehydes first. And what this does is it allows us to preform the enolate with LDA, fully converting one of the compounds into the enolate, which means none of that compound will then be available as an electrophile. We then add the other compound very slowly to the enolate, the electrophilic carbonyl very slowly to the enolate, and then this will form the desired product. The aldol reaction can also undergo an intramolecular variety, and this is going to be where we have both the aldehyde or ketone in the same molecule. So in this example, we can take this ketone and form the enolate on one alpha carbon, and then that will go ahead and attack the other carbonyl group on the other side of the molecule. This will always result in a ring, and generally will form 5 and 6 membered rings. 5 and 6 membered rings almost always form the fastest, and so this reaction will only work in an intramolecular variation where a 5 and 6 membered ring is formed. The next reaction we will look at is the Claisen condensation. The Claisen condensation is very similar to the aldol condensation, except instead of using a ketone or aldehyde as a starting material, we're going to use an ester. It's a nucleophilic acyl substitution reaction where the nucleophile will be the enolate of the ester and the electrophile will be the ester. So it's quite analogous to an aldol reaction. And the product for this will be a beta keto ester. And we can look at the mechanism of the reaction. We begin by initiating a proton transfer, which forms our enolate. The enolate can then undergo nucleophilic attack of the carbonyl of the ester, creating our scaffold of the product. The O- will then collapse down and eject out the OR group of the initial ester. So this will then form a 1,3-dicarbonyl compound. The OR- that was then ejected can then nucleophile the doubly alpha proton to form an enolate anion, which is stabilized by 2 carbonyl groups. And so because this last step occurs, this is going to be what drives the reaction forward. And in order for us to reprotonate this very stable negative charge, because it's next to two carbonyl groups, we're going to need an acidic workup to obtain the neutral compound. There are a couple limitations to the Claisen condensation. First of all, the starting ester must have two alpha protons, and it's because when we looked at the mechanism, the last step was that deprotonation by the alkoxide ion, and that's what's going to drive our equilibrium of the reaction forward. And then second, we can't use a hydroxide as a base to promote the Claisen condensation because hydroxide will hydrolyze our ester, which we learned about last chapter. The final limitation of this reaction is that the alkoxide that we use must match the OR group of the ester, otherwise we will obtain transesterification when we have the base attack the carbonyl compound and eject out the other group, so then we would end up with a mixture of the two products, which we don't want. Just like we had crossed aldol condensations, we can also obtain crossed Claisen condensations, but their utility is far less than the aldol. In order for these to be useful, one of the esters must have no alpha protons, or we'll have to use a directed Claisen condensation with LDA as a base. We can also obtain an intramolecular Claisen condensation, and this is called a Dieckmann condensation, where we take an ester, a diester in one molecule, and convert it to the cyclic form. And similar to cyclic aldol reactions, the Dieckmann cyclization will only form 5 or 6 membered rings. So we're going to change gears a little bit and look at alkylations at the alpha position. So this, you could think about this similar to how we did a bromination at this position. This is going to undergo an SN2 mechanism, but in our first set of the reaction, we're going to create the enolate, like with LDA, and then with an alkyl halide, we can use the negative charge of the enolate that's formed as the nucleophile in our SN2 reaction. We will have the typical SN2 restrictions, where it works really well with primary or secondary alkyl halides, but when we have secondary or tertiary alkyl halides, in some cases, the elimination will dominate. So in that case, we can have also the aldol reaction competing with the desired alkylation. So we must use LDA as a strong base. And if we have an unsymmetrical ketone, we'll have to discuss regioselectivity because there'll be two different enolates that can form, and we'll take a look at that. If we have a substituted alpha position on one side and an unsubstitution on one side, then we have two enolates that can form. The thermodynamic enolate will be the more stable enolate, and the kinetic enolate will form faster, but it's less stable. So this would be the kinetic enolate. And if we look at the reaction pathways in the presence of base, right, the kinetic enolate will form the fastest because it has the lowest amount of energy needed to reach its transition state, but the thermodynamic enolate will form over time. It just requires a larger amount of energy input. And since this is a reversible process, the longer we leave the reaction sitting at a higher temperature, then we can achieve the thermodynamic enolate. So if we do want to obtain the kinetic enolate, then we need to use irreversible conditions like deprotonate with LDA at -78, and this fully prevents the enolate from forming in the thermodynamic position because we've reduced the temperature so much. And then we add in our electrophile. If we use sodium hydride at room temperature, then we're using reversible conditions, and we will end up alkylating at the more substituted position. So this allows us to alkylate at both the less substituted and the more substituted position, depending on which set of conditions we use and whether we push the reaction towards the kinetic or the thermodynamic product. In the malonic ester synthesis, we can convert an alkyl halide into a carboxylic acid with two additional carbons. In this case, we'll start with diethyl malonate, and we'll form our enolate. And this will be actually a really stable enolate because it's stabilized by two ester groups, so it's doubly alpha. At this point, we can then react the enolate with the alkyl halide to form our new carbon-carbon bond. In the presence of acid, we'll hydrolyze both of the ester groups into carboxylic acids. In the presence of heat, one of the carboxylic acid groups is then decarboxylated, and you can see the mechanism here. It's a 6-electron, 6-membered ring transition state, which leads to an diol, which is also an enol that can then tautomerize back into a carboxylic acid. So overall, the malonic ester synthesis allows us to add 2 additional carbons and a carboxylic acid to an alkyl halide. First step, we form our enolate. And the second step, we do our SN2 reaction. And then the third step is we hydrolyze in heat. Diethyl malonates can also be used for a dialkylation. And in this case, we will use base and one alkyl group to add one. And then we use a second equivalent of base and the second alkyl group to add the second. At this point, we can then do our acid and heat to decarboxylate and give us our product. The acetoacetic ester synthesis is analogous to the malonate synthesis, and this will convert an alkyl halide to a methyl ketone. So in this case, we will obtain 3 additional carbon atoms. We begin the sequence the same way, create the enolate, do our alkyl halide, and then use acid and heat to decarboxylate to yield the final product. So depending if we use the acetoacetic ester or if we use the malonate, we can obtain 2 additional or 3 additional carbons. So the next set of reactions we're going to look at is going to use a different electrophile than the aldol condensation. It's actually going to use the product of the aldol condensation as the electrophile for this reaction. So if we look at the product of the aldol condensation, it is an alpha-beta unsaturated aldehyde. That means between the alpha and beta carbon, we have an alkene. And this is also called a conjugated carbonyl group because the alkene is in conjugation. We can see that in the resonance here. We have a resonance contributor that puts a positive charge on the carbonyl carbon. But there's one additional resonance contributor that puts a positive charge on the beta carbon. And so this we can think of as our electrophile for this next reaction. The beta carbon is electrophilic as well and will have a partial positive charge just like the carbonyl carbon. So depending on what nucleophile we use, we can have nucleophilic attack at the beta carbon or the carbonyl carbon. So if we use a Grignard reagent, this is going to generally attack the carbonyl carbon, and this is called a 1,2 addition reaction. If we use a Gilman reagent or an organocuprate reagent, then the nucleophile will attack the beta carbon, and this will be called a 1,4 addition or a conjugate addition. So we can look at the general mechanism for a conjugate addition, which is where we have a nucleophile that's going to create a new bond with the beta position. Then these electrons will move up and form the enolate. Our enolate can then be protonated, which forms the enol, and after tautomerization will reform our carbonyl group. So depending if we use certain nucleophiles, we'll obtain either the 1,2 addition or the 1,4 addition. A stronger nucleophile is going to push towards a 1,2 addition, and less reactive nucleophiles will tend to do conjugate addition because it's less sterically hindered. Often enolates will give a mixture of 1,2 and 1,4 addition products. However, a stabilized enolate will give 1,4 addition products exclusively. So you can see here we have an enolate that's going to form from 2 ketones, so this will be a very stable enolate, and we've talked about this before. But then, when it attacks the conjugated aldehyde, it's going to only do 1,4 addition and attack at this position. So the addition of an enolate to a alpha beta unsaturated aldehyde or ketone is called a Michael reaction. A Michael donor is going to be a nucleophile that does the conjugate addition reactor, or our enolate, and the Michael acceptor is going to be the alpha beta unsaturated carbonyl compound that we use. So here are a list of the reagents that can be used for the Michael reaction. A handful of Michael donors. Notice these are all stabilized enolates, except for the copper species and this stabilized negative charge here with the nitro group. And then our Michael acceptors are all alpha beta unsaturated carbonyl compounds or alpha beta unsaturated electrophiles like this nitro and this nitrile that still create a positive charge on the beta carbon. So the last reaction that we're going to look at is the Stork enamine synthesis. Singly stabilized enolates do not give high yields in the Michael additions. Remember, we only had high yields when we used the enolates that were stabilized by 2 carbonyl groups. So in the Gilbert-Stork enamine synthesis, we're going to be using an enamine as an intermediate. And we can see here how the enamine is made. We condense a amine with acid to create the enamine, and it has to be a secondary amine. This molecule is going to behave very similar to an enolate and create a nucleophilic position and the alpha position. And so this is going to be a Michael donor, but it's a little bit less nucleophilic than an enolate. In a conjugate addition reaction, we can first undergo our conjugate addition reaction. So our enamine acts as our nucleophile, and then the Michael acceptor acts as the electrophile, and we create our new bond. In the workup stage, we have our iminium ion and our enolate anion. When we add acid, we're actually going to hydrolyze our iminium ion back to the ketone. So in this case, the enamine is just a temporary intermediate that we can use to be able to execute this Michael addition reaction. So overall, we have 3 steps. First is formation of the enamine, then we do the Michael addition, and then we hydrolyze back to our ketone.